Hello everyone, I'm presenting today on progress in energy applications of Solvate Ionic liquids SILs. I'd like to acknowledge my supervisors, Professor Luke Henderson and Dr. Bhagyadam Masiri from Deakin University's Institute for Frontier Materials, and Dr. Dan Ekins from the Commonwealth Scientific Industrial Research Organisation in Australia, CSIRO. Carbon fibre is used in aerospace industries, it's used in high-end automobiles. Its largest use by sector is in wind turbine blades, and it's also used in hydrogen pressure vessels. It's primarily used as a lightweighting application to remove parasitic mass. But can carbon fibre be used as more than just a way to decrease weight? So if you envisage an automobile with carbon fibre components, we can actually incorporate structural energy storage panels that are made from carbon fibre in components like the door or in the bonnet panels. So what do these look like? So the most simple form of structural energy storage is a structural capacitor or structural supercapacitor, and these consist of two layers of carbon fibre which act as conductive electrodes, separated by glass fibre which acts as the separator and keeps the electrodes from shorting out. And this system is held together by a bicontinuous two-phase solid polymer electrolyte. So you can see this visualized over here on the top right, where basically the solid resin phase is visible, and this traps and encapsulates a liquid solvate ionic liquid electrolyte phase. So this is what the solid polymer electrolyte looks like under scanning electron microscopy. So this is a washed sample which has the ionic liquid washed out of it, and you can see the porous resin network is left, and basically within this porous system is where the liquid electrolyte is trapped. So at a lab scale, this is what a prototype capacitor device looks like. It uses a glass fibre filter paper as a separator, and it consists of 70% solvate ionic liquid electrolyte with 30% epoxy resin. And we use copper current collectors to act as electrodes in this system and connect to our battery testing setup. So solvate ionic liquids are a three-part ionic liquid. They consist of a metal cation connected or interacting with an anion in solid salt form, which is dissolved in a liquid ether glyme, and this ether chelates the metal cation, and the anion is a pseudo spectator in the system, which it does interact with some of the cation and oxygen atoms as well. Solvate ionic liquids are easy to make. So you take a lithium salt, you dissolve it in an ether glyme system, and you end up with a solvate ionic liquid. They're relatively cheap compared to some traditional ionic liquids, and they're relatively new, first reported by a Japanese research group in 2010. So solvate ionic liquids are highly tunable. You can switch out the ether ligands in these systems, you can switch out the metal cations in these systems, and in particular if you move to higher charge or larger cations than lithium, you change the melting point of these systems and make them more of a molten salt when you're looking at something like magnesium, whereas it's more a liquid with the lithium. And you can change out the anions in these systems. So we've got BF4, PF6, DFOB in the top right, TFSI and FSI here. And something to note with these systems, a limitation with these systems, is that there has been exploration into non-halogenated anions like boroxyalatoborate or BOB, and the sulfame anion. A good example of this is potassium asulfame. However, these are not soluble in the ether ligand or ether glymes, so you know this is a limitation of the solvate ionic liquid system, that the salt has to be soluble in the ether system in order for the chelation to occur. And the current working hypothesis for this is that there is a degree of halogenation that is required. So the attempt to make non-halogenated solvate ionic liquids is a work in progress, but it is not necessarily possible. So if we come back to these bicontinuous solid polymer electrolyte systems, they are two phases. So we assess the mechanical properties through flexural 3-point bend testing, and the electrochemical properties through electroimpedance spectroscopy, EIS testing, and you can see the sample here sandwiched in a battery testing clip with some copper battery testing plates. So in the early work of my PhD, I evaluated the solvate ionic liquids within polymer matrices with increasing lithium content, or lithium salt content I should say. So you can see over here on the right that the 1-to-1 ratio is far less viscous than the 1-to-2 ratio over here on the right, and basically the double the amount of the lithium salt, of double the amount of lithium and the TFSI anion, results in a much more viscous solution. And if we look at this plot here, you can see that the least viscous solution of the G4 1-to-1 sample at 70% solvate ionic liquid content in with 30% resin in the solid polymer electrolyte, it has the lowest mechanical properties of the samples, but the highest ionic conductivity of the samples, which is consistent with it being low in viscosity. Whereas if we move across to the G4 1-to-2 sample, it's far more viscous and has better mechanical properties than the 1-to-1 sample. However, it has lower ionic conductivity because it is more viscous. So what happens if we change the content of the resin in these systems? If we increase the resin content, do we improve the mechanical properties? So you can see here that there is a general trend of improving mechanical properties with reduced ionic conductivity properties, with increasing the resin content and reducing the electrolyte solvate ionic liquid content. However, there is a limit to this, and you can see here that when we tested the 50% samples, it was quite clear that the drop of ionic conductivity by more than 3 orders of magnitude was a result of the percolation threshold being was a result of being below the percolation threshold in the electrolyte system, where basically the conductive channels within the electrolyte were not connecting efficiently, and that explains the significant drop in ionic conductivity. And you can see here that there was an improvement in mechanical properties with the increasing resin content. However, it is depending on the application, this may be suitable or desirable. However, there is a sacrifice in the ionic conductivity electrochemical properties of the systems. So if we compare the different ether ligand systems in the solid polymer electrolytes, the G4 system has greater than 2 times the ionic conductivity of the G3 system. And this is consistent with the G4 system that chelates the lithium less strongly and allows for lithium hopping, particularly at higher temperatures, and allows for the lithium to be held less strongly and the overall system to be higher in conductivity. Whereas the G3 system chelates that lithium more tightly, and actually the G3 ether ligand fits the lithium better than the G4 system. So what happens if these are applied in capacitor devices and energy storage devices? Well, you can see here that the capacitance of the G4 system is actually 22% greater than the G3 system when applied in prototype capacitor devices. And this is purely because the electrolyte is more efficient and allows the capacitor to charge more efficiently and discharge more efficiently with lower resistivity. So neither of the two capacitance storage mechanisms, pseudocapacitance was not changed, so they were not redox active functional groups that were added to the surface of the carbon fiber, for example, that changed pseudocapacitance, and the surface of the carbon fiber, the surface area wasn't increased, so electric AA capacitance, EDLC, was not increased. However, the actual overall efficiency of the electrolyte contributed to improved capacitance in these systems. So if these prototype capacitor devices were applied as structural components in vehicles, we would obviously need to think about the end life application of these electrolytes, because obviously, you know, there's going to be damage at some point to these vehicle components, and we need to know that we're able to recover the electrolyte, which is obviously, it's cheaper. Solvate ionic liquids are cheaper compared to traditional electrolytes, but if we can increase the number of life cycles these electrolytes have, we obviously reduce the emissions and the cost of using these at a larger scale. So the bicontinuous electrolyte system is two phases, a liquid phase trapped within a solid resin phase. So theoretically, this can be separated through simple physical separation. And we wanted to evaluate this purely with the matrix. So we took the matrix without the fibre and we blended it. And we published a paper on this work, and basically we used a NutriBullet kitchen blender, which we were well and truly pushing to the limit. So we were needing to give the blender ice baths because we were sort of blending it for 5 minutes and definitely voiding our warranty. But it worked well, and we certainly haven't repurposed it for smoothies in the office because it's you know, kept in the lab, but it did a good job. And so we blended it with ethanol, which was chosen to be a more environmental solvent with it, while having a high vapor pressure that allowed us to take it off under vacuum. And we initially vacuum filtered the blended filtrate and removed the filter cake basically from the liquid electrolyte, and we did multiple washes of this to improve efficiency over time. We then removed the ethanol on a rotary evaporator and dried the solution, because these, like any ionic liquid, Solvate ionic liquids quite like water, and the samples have been exposed to normal atmosphere during the processing, and we need to remove any residual water. And we ended up with ionic liquid recovered. And you can see here that the blue tint is actually from the amine hardener dye in the resin, and it wasn't visible on nuclear magnetic resonance spectroscopy or Fourier transform infrared (FTIR). However, it was clearly visible in the visible spectrum, because you could see a bit of a blue tint. So I did this once, and I recovered greater than 70% of the electrolyte that was put into the system. And I told my boss about this, and my boss said, "This is great, but can you repeat it 5 times? Is this actually reproducible, or is it a fluke, basically?" So I went back to the drawing board. I made 5 times the electrolyte that I'd ever made before, did this, scaled up massively, and I repeated the process 5 times. And with scaling up, we actually increased the yield, and on average, out of the 5 cycles, I recovered 88% of the electrolyte that was put into the system. We also wanted to focus on other chemicals used in the system, so assessed the ethanol content that was used, and we recovered 83% of the ethanol that was put into the cycle. But we didn't want to stop there. We had this blended resin pulp, which clearly had some ionic liquid left over in it because there was an excess mass of resin. Obviously, if this was applied in an industrial scale, we would try and get that 128% back down to 100% with multiple washes, and improve our yield of electrolyte recovered in this system. So we came up with this idea of encapsulating the blended resin pulp as a filler in resin as a second life application. And I did this, and I actually found that the blended resin pulp used as 10 weight % filler actually improves the mechanical properties of the resin control. So why was this? So I did SEM of the fracture surfaces to try and understand the debonding and basically the processes that were occurring, and it was hypothesized that there was a stronger interfacial bonding with the epoxy matrix with the blended resin pulp particles, and the resin pulp was acting as a reinforcing agent, deflecting cracks in the break areas. So coming back to the fundamental properties of ionic liquids, anyone who's worked with lithium trifluorosulfonylamide, lithium TFSI, knows that it is quite corrosive. You store it in the bases cabinet. However, if these ionic liquids were to be applied in a large scale, we'd really want to know what materials they were compatible with. Traditional ionic liquids have been evaluated for their corrosion inhibition properties. We initially wanted to evaluate the lithium TFSI salt in the Solvate Ionic liquid systems to see if it was compatible with stainless steel, and we compared it against 1 molar hydrochloric acid, HCl, initially for a 24-hour immersion test, and we found that the samples immersed in the Solvate Ionic liquids were consistent with the pristine polished stainless steel and didn't show the pitting and corrosion that the sample immersed in the hydrochloric acid exhibited. We then didn't want to stop here. We actually wanted to look at to see if these ionic liquids inhibited corrosion in corrosive environments. So I did some weight loss testing. Anyone who's done weight loss testing with stainless steel knows that this requires a lot of sanding, very consistent sanding of the samples to remove the oxide layer. We compared it against 1 molar HCl, and you can see the samples here show less corroded regions and corrosion products on the surface, which then have to be removed in order to calculate the weight loss, and that's where the sanding comes in. So this data really showed great macro level properties of the Solvate Ionic liquids as corrosion inhibitors, and the even at very low concentrations, 100 ppm was literally a drop in the volumetric flask of the ionic liquid in the 1 molar HCl solution, and you can see here the increased area where the stainless steel sample was not corroded, where it remained pristine, was greater in the G3 sample than the G4 sample. So to probe the mechanism of this, I did electroimpedance spectroscopy testing, EIS, and I fitted these curves and found that the data was consistent with the G3 system having a greater inhibition on the corrosion mechanism than the G4 system. So why was this? So this was basically because the charge transfer resistance was greater when the inhibitor was present. So basically the Solvate Ionic liquid was creating some sort of film on the surface of the stainless steel, and it was increasing the resistivity of basically the corrosion mechanism. So coming to the fundamental properties of the Solvate Ionic liquid systems, we had some capacitors that exhibited some interesting properties when they were bent. And initially, one of my supervisors, Dr. Baki Damasiri, published a paper on this, and to probe this mechanism more, we actually published a work where we found the Solvate Ionic liquids in their pure form and also within the solid polymer electrolyte matrices were actually piezoelectric. So they released an electric charge under compression. And we, one of my team members, Jean Simon, created this fantastic graphic image for the cover of Materials Horizons with the Aurora Australis in the background for a bit of an Australian themed cover image. So in this paper that Jean worked on, basically he compressed the Solvate Ionic liquid in both the pure form and within the solid polymer electrolyte, and he found that there was a proportionate response of open circuit potential of in millivolts released by the compressed Solvate Ionic liquid and solid polymer electrolyte, and that was proportional to force, which is quite exciting. And we're doing further work with collaborators to understand the mechanism behind this. So what effect does the Solvate Ionic liquid have when it is applied within the epoxy resin solid polymer electrolyte systems? So other than being conductive, as I've mentioned previously, and other than the, I mentioned the Solvate Ionic liquids dominate the their viscosity dominate the mechanical properties of the 70% ionic liquid and 30% resin solid polymer electrolyte systems. The solvate ionic liquid actually catalyzes the curing of the epoxy resin systems, and does this by assisting in the ring opening reactions of the epoxy resin. So I assessed this in a paper where we looked at using rheology. We looked at the curing times and the reduction of gel point in these systems, and we found that the G3 ligand significantly reduced the gel time, or basically increased, or was more active in catalytic curing than the G4 system. And when we increase the lithium TFSI content in the, or molar ratio in these systems, we actually got a catalytic curing rate of over 90% reduction when we went up to the 1 to 2 systems. So this has pros and cons. The advantage of this is that the resin can cure quite fast, and we could potentially have very effective fast industrial scale curing of these systems when applied in electrolytes. The disadvantage is that when you get up to sort of the 80-90% curing rates, reduction in gel point times, you obviously are having issues with void formation, and you can't degas the resin, which of course creates mechanical weaknesses in the system. So in order to try and improve our mechanical properties and improve basically the homogeneity of these systems, so basically we can mix them more efficiently with basically using a system that would not have a reduced gel time due to the catalytic curing, we looked into UV resin systems. So to improve mixing and homogeneity, we mixed using a Tinky mixer, centrifugal mixer, which of course, because we were using a resin system that didn't have catalytic curing from the solvate ionic liquid, we were able to mix these systems much more homogeneously, and also do degassing using the centrifugal mixer. This picture over on the right shows these samples being cured under a UV light. And we actually initially, after doing some prototype testing of evaluating these samples in basically mold cured resin to see if they were conductive, see what their mechanical properties were, we actually, our research group scaled up to actually 3D print these systems using a off-the-shelf commercially available 3D printer, which was very exciting. So we evaluated the mechanical properties of these 3D printed systems. We did them at varying resin contents. So we used 70% electrolyte content and 30% resin, 60% electrolyte content, 40% resin, and 80% electrolyte content and 20% resin. And you can see at the higher electrolyte contents, the ionic conductivity is much higher than at the lower electrolyte contents, and the mechanical properties are sort of the inverse of that, basically, with much higher mechanical properties with the 60% electrolyte content, and much lower with the 80% content. And something that was really cool with this was that when we actually compared the properties from the 70% epoxy resin system versus the mold cured system versus the 3D printed system, we actually saw at a 70% content an upward trend where basically there was greater homogeneity in the basically the pixel by pixel printed system versus the mold cured bulk UV cured system, and these had improved mechanical and electrochemical ionic conductivity properties compared to the prior system we'd used, which was the epoxy resin system. And this graph in the bottom right here has the same error bars plotted for all three samples. It is just that the UV cured systems have much greater homogeneity, so the error bars are actually smaller than the graph symbols on this plot. So that really shows the difference, and and the pros of basically the benefit of moving away from that epoxy resin cured system where we had issues with the catalytic curing, we couldn't degas the resin, and we moved to a system where we could mix homogeneously, degas efficiently, and cure initially in the mold cured system as a bulk efficiently, and then actually make a stronger material when we cured line by line in the 3D printing technique. So we also printed a fit together capacitor that had no separator, and we evaluated the capacitance of this through cyclic voltammetry and GCD, galvanostatic charge discharge. And basically this was a really cool prototype, basically highlighting how we could upscale our current systems to be potentially industrially viable fast capacitor systems, which is quite exciting. So I might also mention that we've also applied within our research group the Solvate Ionic liquids within structural battery systems, and we applied the optimized G4 system in this. So initially we started off with the G3 system in capacitors, and we now have applied the optimized G4 system within our battery devices, which is very exciting. I might mention that we published earlier this year a review paper on Solvate Ionic liquids, so I encourage you to check this out if you are considering working on Solvate Ionic liquids, or if you have chemical systems or processes that you would like to potentially expand to be used with Solvate Ionic liquids. I'd like to acknowledge my supervisors, in particular the graphic design team who contributed to many of the beautiful diagrams in this presentation. Thank you.